Can you make a comment about the negative dimensions?
Yeah, so it's a very technical thing, and did I? Yeah, I'll put the link to it. I think I put it in the notes already, but it's a very technical thing that when you have linear problems, then you can try to do following thing. You can try to increase dimensionality of the problem in such a way that the effect is that it subtracts the degree of freedom, even though you added it. And this is done technically by demanding that you don't have numbers that we are used to, but Grassmann numbers, which have a property that, if you square them, you get -1 than 1 in some sense. So, so it's a technical thing. Now, you can implement it explicitly in calculations of kind that we do with our Gaussians, that if you have when you evaluate a Gaussian of some covariance, result is square root of determinant of the covariance. We have done this lots of times. And that has an interpretation that you're computing the volume of that guy. We have also done lots of cases in which we have a symmetry and we divide the space into blocks. So the determinant is a product of determinants for each block. Now, you can ask yourself, what happens when I take a ratio of determinants? And there are good reasons why to look at the ratio of determinants. Then by our famous formula, that the ratio of determinants is, ratio of determinants says I'm measuring the volume in units of some other volume. So that's one way to think of it. But also turns out sometimes another interpretation is that you use the formula that trace log equals log of determinant. And when you do this upstairs in these traces, you get eigenvalues of first determinant subtracted by the eigenvalues of the other one, because it was 1 over determinant, it took a log of -1. So you find out that when you're looking at eigenvalues of the operator, all the eigenvalues you have are there, but you subtract the other ones. And that is another way of implementing this subtraction. So it says, when I compute the trace, it used to be 7, like dimension of the space. But now I have to subtract the 2 dimensions, the famous negative dimensions. And even though I believe I'm in 2 spaces, one that's called supersymmetry, or, I have 7 good dimensions, but there is this weird world of negative dimensions there, -2. And they have this different statistics that says when I take a trace, I get a negative number rather than a positive number. And now the whole space has dimension 5, even though I have 7 -2. And so the negative dimensions come in. Then, you say, well, then there's a physical interpretation. It says, I had a photon, so it looked like a vector, so it had to have 3 coordinates. But it turns out it only has 2. It's massless. So it's transverse. So what do I do? So what I do is I pretend it's 3, but I subtract 1. Then that's called ghost. I introduce a particle whose only purpose is to subtract the wrong direction. So these are all variants of negative dimension. So they're used in calculations all the time. And you can just take them as calculational devices, or you can try to give it more meaning. So what Penrose noticed, if he did calculations in -2 dimensions, they are much faster than in plus 2 dimension. So that paper was about that. That was also the first paper where he showed how he actually computes with drawing pictures. But it took him 17 years of hiding it because he realized he's not like the other people, because other people seem to understand equations as he didn't. So he had to draw them. And it turns out once you can publish it, there are lots of visual people, so lots of people find it useful. So if you work for Professor Abel, he does that all the time. He draws this out because they're natural language for his calculation.
Yeah.
And this for the same reason. I mean, Penrose had to study tensors, and Abel has to study tensors. That's a natural notation for that.